And we looked at key terms: random experiment outcomes, the sample space, equally likely outcomes, what an event is, but also deeply we understood what statistical inferences are, and we looked at how we can actually make some of the statistical inferences in probability. And we looked at some of the common inferential methods, looking at hypothesis testing, confidence intervals, regression modeling, and the margins of error. And then we went ahead to look at the aspect of the approaches to probability, looking at classical, relative, and subjective probability, where we'll say the classical looks at all possible outcomes being equally likely to occur. And then we were able to look at this dice tossing as an example, but also we looked at relative, where we said relative looks at a period of time, meaning we're looking at probably a period that is 5 years, or we're looking at a monthly data, maybe over 12 months or a quarter. But I would say it looks at a relative data that can help us understand the incidences of disease as an example in there. Then lastly, we looked at the subjective judgment, where we said it is intuitive and it is according to an individual's belief on an event. And we were able to look at an example that looks at a football team and how someone can place a probability on a win for that particular team in there. So today we want to look at what we call a basic probability notation. This is just one of the topic or one of the sub areas that we want to look at. We may not take a lot of time because they are just short ideas in here. So one is in basic probability notation, we're looking at the representation of the likelihood of an event to occur. For example, we want to look at if we wanted to look at the probability of getting a flu shot being equal to 0.75 or what we call 75%, then we would interpret it basically as there is a 75% chance of getting a flu shot. Or here we're looking at an aspect of getting a vaccine. So in basic probability notation, you're looking at an interpretation of a notation. Remember when we were talking about the P, we said that it is looking at a thesis, or what we call a hypothesis, that tries to look at the chances of an individual, in this case taking a COVID or a flu jab. So if, for example, we are saying the probability of getting a flu shot is 75%, in other words, we are interpreting in a basic probability notation, we are interpreting that notation as a 75% chance of getting a flu shot. So for people who are doing reproductive health, if you did a basic probability notation on the number or the percentage of antenatal visits, you wanted to look at, for example, if you said what is the probability of mothers attaining eight antenatal visits, you would have to look at the probability of attending 1 antenatal, 2, 3, 4. And drastically, if you had data to look at antenatal attendance, you would drastically see that the probability reduces as the number of visits increase, meaning the chances that women would come for the first antenatal visit could be about 0.8, 0.7, around there. But as the visits increase, maybe to the second visit, to the third visit, to the fourth visit, you will realize that the probability of attending these antenatal visits would be reducing, and the probability that an individual might attend an eighth visit can go 0.2 around there. So it is upon you as a specialist in that area, having understood having gone through a probability class, to be able to understand and interpret this and design specific interventions to try and address these issues in the community. Then two, we want to look at what we call the complement notation. And here we are saying, we are looking at a notation saying the probability that it is not A, that someone is not having a particular disease. So here we're saying it represents the probability of an event not happening, which is the opposite of event A. For example, we would say, what is the probability of not having diabetes? Then it would mean to be able to get the probability of not having diabetes, you would say it is 1 minus the probability of having diabetes. So that is what we call a complementary notation, meaning we're looking at the opposite of the event. What is the probability of being pregnant? Then the other notation is the probability of not being pregnant. Also, if someone is pregnant, we would say, what is the probability of having a live birth and having a stillbirth? So those are the contextual issues when you're looking at complementary. Complementary, we're looking at two aspects in that case. So for example, if the probability of getting a disease is 0.2, then the complementary probability of not getting the disease would be 0.8. And meaning we're giving you an idea of what you could actually use to determine some of the issues in your community, not only in your community, but also in your health setting or in your workplace setting. For example, if you're doing marketing of a product, for those who could be business students, if you're doing a marketing of a product and you realize that the sales of this particular product are lower, then you should be able to, in a week, you should be able to project the probability that you're going to have sales. You should be able to do that projection and then be able to suggest ways that you could help to improve such. So complement probability can be very useful in public health to estimate the risk and benefits of different interventions or policy. For example, if a vaccine has a 90% efficacy, then the complement probability of getting infected after vaccination is 10%. So then this can help compare the vaccine with other options or with no action at all. So for any intervention, you should be able to understand the level of efficiency that the intervention would create. So in this regard, if you're looking at a vaccination, or possibly if you're looking at introduction or using of a face mask in the prevention of let us say flu, then you should be able to understand what is the efficacy level of using a face mask. If it is about 60%, then the 40% still has a room for someone to get the infection. Similarly, if you're looking at SMC, what they are calling safe male circumcision, I think nowadays they're using a different term, and they're saying its protection against HIV is about 60%, then you should be able to note, as a public health expert, you cannot definitely only encourage safe male circumcision, but then you will also have to encourage other measures of protection, because then 40% is still a very high chance of infection that can occur. So this aspect of complementary notation, not only but generally probability, is very important in trying to understand interventions and policy, but also to try and understand behavior of communities towards particular interventions. So there is what we call conditional probability notation, where we are saying that the probability of B occurring, uh, uh, given that event A has occurred. So the conditional probability notation represents the likelihood of event B occurring given that the event A has occurred. For example, that an individual who tests positive for high blood pressure would definitely test positive for diabetes. And that is just an example. Like here, you're looking at testing positive vis-a-vis a risk factor. There are chances not until the EID section of handling HIV infections occurred in the earlier years. It would mean that if a child was born to a HIV positive mother, definitely the child would be a HIV positive in that regard. So this is what conditional probability notation happens. So, for example, in reproductive health, you should be able to know that if this person takes a contraceptive, and then there is going to be no conception. Similarly, if a positive person has intercourse that is unprotected with someone who is negative, then you should be saying the risk factor is having had unprotected intercourse, then the testing would be positive. So similarly, you should be able to apply this in aspects of antenatal care also, that mothers who do not have their first visit, then, for example, in village A, if child had visit, then it is likely that they will also not have, in the next years, they may also not have, if no intervention has been carried. Similarly, if someone's mother did not conceive or did not deliver at a health facility, then that is the risk factor, and then the probability that the person will also not produce or deliver at a health facility are in there. So we are saying that, for example, the probability of testing positive for a disease when having a particular risk factor is equal to 0.20 or 20%. Therefore, the interpretation would mean that the probability of testing positive for the disease when having a risk factor is 20%. So let us say, what is the risk factor of getting which disease is common? The risk factor of getting malaria is a treated mosquito net. So we would say here that the probability of having a positive malaria case when not sleeping under a mosquito net is 50%. So that is a conditional probability in there. Then there's joint probability notation, where we look at the aspects of probability of A and B. Now, joint probability notation represents the likelihood of both events occurring, meaning event A and B can occur simultaneously. A and B. It can be B and A. So joint happening simultaneously. It can be used and they are combined likelihoods. For example, we're saying that the co-occurrence of two diseases per se, let us 1,000 individuals in a study, 150 have both diabetes and hypertension. So using joint probability, the probability of both A and B occurring would be the number of both diseases. So we are looking at 150. That is both diabetes and hypertension. And as your denominator, you're putting the population that is susceptible to this particular kind of disease. So then your probability of getting either diabetes or hypertension or the joint diseases from both. So in this case, if you wanted to look at the probability that the person who has uh, the probability that that population might have both diseases, you would subject the cases. For example, you have to go to a health facility and look at who has fever and malaria. So who has fever and malaria? Who has fever and malaria? Or you look at another condition that is probably jointly associated to malaria, or most cases we can look at malaria and pregnancy. So you would look at pregnancy and malaria, Then you would be able to determine the number of malaria pregnancies, malaria that you would get in that particular population. And therefore, if you're able to look at such a probability, then you should be, as a planner at your health facility, you should be able to know that in this particular month, these are the number of malaria in pregnancy that I will get. And that is very key for your planning purposes. But this joint probability notation limitations, and therefore joint probability focuses on concurrence of events and may not provide information on the individual probabilities. So in this case, you may not look at an individual alone because it is looking at it is generalizing the probability that someone will get both diseases concurrently. So it assumes that the events are the ones that are independent, which may not be always be the case. So sometimes the events may not be very independent. So if it assumes that someone will get diabetes, then after get high blood pressure, that assumption becomes a criticism, because sometimes the events are not necessarily that independent as it states. So another very important aspect of probability is what we call the additive probability for mutually exclusive events. Now, additive probability is used when events are mutually exclusive, meaning they cannot happen at the same time. For example, you cannot have a live birth. We're looking at a single pregnancy. You cannot have a live birth and a death at the same time. So it is one event at a time, meaning you can either have a live birth or not. So in additive probability, it is either A or B. It is either a win or a loss. So that is what additive probability means. So for example, if you wanted to look at a subset, let us say the outcome of one event is 1, 2, 3. Then the outcome of the other event is 4, 5, and 6. So these are what we call mutually exclusive events, because they do not contain they do not have any outcome that is related. Examples of vaccination for two diseases, let's say influenza and measles. Now, these diseases are mutually exclusive because a person cannot get both vaccines at the same time. So, assuming that the probability is about 0.6, meaning that there is a 60% chance of an individual getting the influenza vaccine, and then let us assume that the probability of an individual receiving the measles vaccine, which is the probability of B, is about 0.45, meaning the measles vaccine. Either influenza or measles vaccine, we use what we call the additive probability formula, where we look at the probability of either A or B will equals to B, which is the probability of A plus the probability of B. Therefore, the probability plus 0.45, giving us 1.05. Now, 1.05 does not make sense in probabilities because we earlier discussed 2 and 1. Now, in this case, the probabilities of receiving the influenza and measles vaccine are being double counted because they are mutually exclusive. We are double counting them because they do not have any similar probability to be able to ascertain the probability of someone being able to get either A or B, because then this person cannot get both. So to find what we call the corrected combined probability, we need to subtract the probability of both vaccines from the sum of individual probabilities. So in this case, we would be able to summarize, we would be able to look at 0.6 0 plus 0.A and B. So if you looked at what we have here, we would be having here we would be having 0.60 plus 0.45, which is the probability of receiving both vaccines. So just for this interpretation, we shall now assume that the probability of an individual receiving both vaccines is 0. We shall do the subtraction as it is. And therefore, it will mean, the interpretation will mean that there is a 10% chance of someone receiving both vaccines. So I will have another example in here. So roughly, you can be able to see this is the explanation. Probability of someone getting B or a vaccine for influenza plus the probability of receiving a measles vaccine divided by subtracted by the probability of A and B to give you 0.95. So the corrected probability of 0.95 represents the influenza or measles vaccine. So we have another example here to explain additive probability for mutually exclusive. The box contains 2 red, 4 green, 5 blue, and 3 yellow marbles. Now, if a single random marble is chosen from the box, what is the probability that it is red or green? Now, from this statement, you actually realize that this is a mutually exclusive event. Why? Because a red marble cannot be green. A green marble cannot be red. A green marble cannot be blue, and a blue marble cannot be yellow. So meaning they are different you can, from one pick, you cannot pick or if you did that single random marble chosen, if you picked it from the box, it cannot be both red, green, or it cannot contain all the other colors. And therefore, the probability of getting a red would mean that we have the probability of getting red would equals to 2 out of 14, meaning we are looking at red, the probability of getting red would be 2, which are the two red marbles, divided by all these other marbles that are in that single box, meaning the probability of getting a red marble would be 1 out of 7. And then the probability of getting a green marble would be 4 divided by 14, which will equals to 2 divided by 7. So the probability of getting either a red or green marble would be 1 able to give you the probability of getting either a red or a green. So having looked at mutually exclusive, we similarly again look at what we call the additive probability for non-mutually exclusive, meaning an opposite of mutually exclusive. Now, additive probability is also used when events are not mutually exclusive, meaning they can happen simultaneously. So additive probability for non-mutually exclusive events means that the probability of A or B will equals to the probability of A plus B and minus the probability of A and B. Giving an example of a disease. Yes, John, you have your hand on. You can ask your question.
I don't know whether the network, the slide is not stable. It's on and off.
Oh, can you be able to see this one?
Yeah, it is appearing and disappearing. I don't know whether it's a network.
Let me try and reshare.
Yes. I'm okay, how are you?
Let me try and reshare with you then. Hopefully there you can see. Are you able to see that slide now? Are you able to see the slide? Anyone can respond. Are you able to see the slide? John?
Not yet.
Not yet. Oh, wow.
Yeah, it's now. It has come now.
Probably the computer is a little slow, or it could be a network problem. So I was just at the verge of explaining the non-mutual exclusive events. And I was saying, for example, the disease screening tests for two conditions were saying diabetes and hypertension. And we're saying that these conditions are not mutually exclusive because a person can have both conditions. So the probability of testing positive for diabetes, assume the probability of testing positive for diabetes is that particular figure, then the interpretation will mean that there is a 20% chance of testing positive for diabetes. And the probability of testing positive for hypertension, assuming that it is 0.3. So there is a 30% chance of testing positive for hypertension in that regard. And therefore, you can be able to calculate the combined probability of testing positive for either diabetes or hypertension. But let me take us to an example here for non-mutually exclusive events. So just in reference to what we are saying is non-mutual, meaning two things can occur at the same time simultaneously. So we are giving an example that in a math class, we have about 30 students. 17 are boys and 13 are girls. You cannot be both a girl and a boy. You can either be a boy or you are a girl. On a unit test, 4 boys and 5 girls made you excuse me for a minute here. So we're looking at we're looking at on a unit test. These people were able to conduct a test, and 4 boys and 5 girls made an A aggregate, meaning they got A in the test that they sat. So if a student is chosen at random from the class, what is the probability of choosing a girl or an A student? So this is what we're calling non-mutually exclusive, meaning you can have two outcomes at a go, meaning you can choose this girl, but at the same time she also got A. So we want to look at that probability of having a diabetic patient who also tested positive for hypertension. So in a practical explanation, if we said that there are 30 clients who came for a test, who came for a test, 17 of them are men and 13 of them are women. So in a test that was conducted, 4 boys and 5 girls tested positive for diabetes. So we are saying we're looking at the non-mutual exclusive event here is that someone can be a girl and test positive, but the person can also be a male and still test positive. So those are two possible outcomes that can occur. So in this regard, for you to be able to calculate the probability of choosing a girl who is or an A student would mean that the probability of choosing a girl would be 13. The 13 girls that are in there divided by the total number of clients, which is 30 students, or which is 30. Then the probability of choosing a student who has A, the probability of a student who has A would be 9 from the total number of pupils or students who had A's, 4 and 5. So you would have 9 out of the total number of out of the total number of students that were there, which is 30. So now you have to look at the probability of getting a girl and an A. So that will be 5 divided by 30, because you're looking at a girl who has A, and in this case there are 5 of them. So to get the probability of choosing a girl or an A student would mean that you're adding the probability of getting a girl plus the probability of getting an A student minus the probability of getting a girl and an A, meaning you're getting 13 out of 30 plus 9 out of 30 minus 5 out of 30 to give you a probability of 17 out of 30. So roughly that is what it is explaining, even in this upper statement that you're seeing up here, that where we are able to say that you're subtracting 0.20 plus 0.30 minus the probability of A and B. to give you the figure that is down here, which is 0.40. So this represents the likelihood of testing positive for either diabetes or hypertension, accounting for the overlap of both conditions. So you should be able to use such a skill in a laboratory to try and understand the number of tests that you can conduct in a community and the number of tests that you conduct. In this particular lecture, we want to look at what we call conditional probability. And in conditional probability, we want to just understand that it calculates the probability of an event happening under a specific condition, or given that another event has occurred. So it is used to assess the likelihood when certain conditions are met. For example, the probability of developing a specific disease given the presence of a risk factor. A group with the risk factors R plus, 8 individuals developed the disease. So the probability of developing the disease given the risk factor is calculated as the probability of developing a disease given the risk R would equals to the number of the disease and the risk factors divided by the total number of risk factors. So here we're looking at, if we said that we have 80 individuals that developed the disease, we would divide it by the total number of people at risk, or a group that is at risk, meaning it will be about 200. So in this case, let us look at probably the diabetes. Should we look at diabetes again? Which condition is there are certain, because of the risk factor associated with HIV, there are certain diseases that they will definitely suffer. For example, possibly aspects of malnutrition. So it will mean in this case, we are having the number of people who have developed the disease being 80, and then we divide by, in this case, 80 we are looking at the ones who have developed malnutrition, divided by 200, and 200 will be the group at risk, which is persons who are living with HIV. So living with HIV will develop malnutrition. Or nevertheless, it is always common that individuals who have high blood pressure will also develop a condition of diabetes, or is diabetic or of stroke. So you would want to understand what is the probability, and for you to understand that particular risk group who have developed the condition, you want to understand. So then you subject the number of people who have gotten that condition to the group that is at risk. Then you're able to get the probability. And in that case, we are saying the probability here is at 0.40 among individuals with the risk factors. And there is a 40% chance of developing the disease in that interpretation in there, because we are saying that a probability ranges from 0 figure to 100%, it would give you 40%. And in conclusion, there are limitations that come along with what we call the conditional probability. And whereas we're saying that whereas conditional probability assumes that the events are related and the outcome is dependent on the condition, it may not provide information about the overall probability of the event without considering the condition. So you have to first consider the condition. You must first know how many people got the condition before you can have the probability of the event occurring. So in any case, if you do not have the number of people who have suffered that specific condition, you may not be as well able to generate the probability. I don't know if we have any questions to what I have discussed in here. If we have any questions, you can raise up your hand and we are able to discuss. If you have a comment, you can as well raise up your hand. Otherwise, from me, it is the end of this particular lecture there. Yes, John.